All right, good afternoon, everyone. We are in the home stretch to happy hour, so get ready. But in the meantime, you're welcome at session 3 of PFAS Forum 4. We got team treatment coming up on deck here, so we got a great lineup of speakers. And I know we've explored treatment technologies a bit earlier today, and so these guys are going to take a deeper dive into treatment, so I'm looking forward to that. We're going to do a couple things. One, I'd prefer to save the questions till the end. So I'll give you a little more time to formulate your question, but I want to make sure everybody gets their talk in today. The second thing we're going to do is we're going to do little fun facts. So I've been coming for the last few years, and we're not doing bios, but it's fun to do fun facts. So I'm going to tee up a couple of those for our team members here today. My name is Chad Northington. I'm a senior project manager with Terracon, and we're going to be starting with Mr. Richard Olliver. And one thing you should know about him is he is a serial entrepreneur, not to be confused with serial killer. He wanted me to reassure you that that's not what he is, but he is a serial entrepreneur, which in his world means he's kind of a low-key kind of guy with doing some films, I understand, CDs, DVDs, music. So that's his I guess, your evening job. So his day job is what he's going to tell us about today. So again, Mr. Richard Olliver with ETA Energy. Take the stage, sir.
Okay, good afternoon, everyone, and thank you, Chad, for that very nice introduction. I would also like to extend thanks to Gene Jones and Swix for once again running a truly excellent conference. I've been to several now, and they're always truly excellent in terms of the material and the people that are attending. I should also say that based on my hobby passion of filmmaking and recording music, that if you come to our booth and drop your business card in it's a Disney cup showing Grumpy, which from time to time describes me, and you will be eligible for receiving a DVD or a CD, and we're going to quietly draw those things tonight, and so we'll let you know by text or cell phone, and you can come by in the morning and pick up your prize if you're selected. I would, at this time, like to share something with you that I learned as recently as last week. Did you know that a slice of pie in Jamaica goes for $6.48, and a slice of pie in the Cayman Islands goes for $7.80? Those are the pirates of the Caribbean. Okay.
Tough crowd. They're loosening up.
Okay, a little background on the presentation because we're very, very unusual here. I am here with my partner with Energy Transaction Advisors, also abbreviated ETA. And essentially, we're going to take a look at commercially available PFAS destruction and remediation technologies in the USA and globally. And it reflects diverse process technologies, feedstocks, and products drawn from our proprietary database of over 200 technologies. The technology shown will be in various stages of commercial development, and supporting data shown indicates it's all within the public domain. Websites indicate that all of these technologies shown are capable of the destruction of PFAS, mainly due to their operating temperatures. The presentation is aimed primarily at gasification, pyrolysis, plasma arc, supercritical water, and hydrothermal technologies for destruction of PFAS and other purposes. As such, we do not reference technologies related to landfill gas, anaerobic digestion, incineration, other than superficially, and other conversion technologies. The presentation is intended to be technology neutral, meaning we're totally totally unaffected by any differences, and we represent that we are totally objective in our analysis of that. And above all, this presentation should not be used for investment purposes. ETA is a boutique consultant with a focus currently on waste, biomass, and plastics conversion. And biomass includes things like waste wood and any other plant material, agricultural materials, and ultimately plastics that are typically waste and looking for a disposal method. And effectively, we're focusing on gasification, pyrolysis, and plasma arc. And our key assignments typically are all what I would refer to as due diligence on behalf of either developers or technology suppliers. And we've been very active over the last year in this particular arena. Just a quick snapshot of the factors globally that are affecting and essentially reshaping the PFAS destruction remediation marketplace. Without going through all of them, I think you recognize all of these social, political, and environmental factors, and I think all of those represent a component of all the activity that is tending to push this technology forward. And the main one, of course, here in the U.S. is recent activity and regulation and rulemaking by the U.S. Environmental Protection Agency, which I think will have a very profound effect going forward on what happens in this industry. You've seen some of these charts earlier, and I'm not going to dwell on them. Basically, what are PFAS? You already know. Most of you know far better than I do what they are. PFAS family tree. Initially, it was started years ago, stood for perfluorinated chemicals, PFC, but in the transition over time, PFC has fallen off the tree, and PFAS is the prominent nomenclature used to describe these forever chemicals. And essentially, where are they found? They're found everywhere: air, water, soil, plants, food, industrial plants, packaging, household products, and many others. And are they safe? I think the clear answer is no, they're not, but the jury is still out, I think, in terms of true health consequences. Okay, how did we get into potentially using gasification, pyrolysis, or some of the other technologies rather than what the traditional methodology has been, which is incineration? And as shown there, most hazardous waste incinerators have operated between 980 and 1200 degrees centigrade. And since the thermal destruction of most organic compounds occurs between 590 and 650 degrees centigrade, I've essentially made a very simple calculation and said, well, gasification, pyrolysis, whatever, all typically operate well above those ranges, and therefore those technologies should be fully capable in its processing to destroy or at least remediate PFAS. Okay, I basically took a look and developed from our internal database of over 200 technologies. I basically developed this list primarily based on the operating temperature of the various technologies. And then I actually took a look at the sponsors and participants here of people that were offering technologies other than incineration and so forth, and they've been added to the list. Let me say that ETA, Scott and I are very familiar with about 2/3 of the companies on this list. We talk to them fairly regularly. And the other third, as you people in the audience, are relatively new to us, and we'd be happy to expand those relationships and get to know you better and have you become a part of our normal parlance going forward. At this point, I'm going to everybody that every technology that I've listed, I've got a slide for each, and essentially I'm going to go through those at pretty high speed. You'll be getting a copy of this, so you'll always have an opportunity to do your own research, and I encourage you to do that. Frontline bioenergy basically is a fluid bed gasification system, and it has a proprietary gas cleanup system which includes the removal of tars, which makes them very unique within the gasification space. They have several projects in development, and typically they're large scale, meaning nominally about 1,000 tons a day of feedstock. And they're based in Nevada, Iowa. I should point out that virtually all of the gasification pyrolysis technologies that I'm describing, their main purpose is not to destroy PFAS, but it's to basically convert whatever feedstock they're taking to something known as synthesis gas, and the acronym is basically syngas, which is an intermediate vapor that can be then converted into other valuable materials, unlike incineration, which becomes dead-ended at the end of its processing. Gasification and pyrolysis allows you to take syngas and convert it to chemicals like hydrogen, methanol, ammonia, SAF, and also convert it to Fischer-Tropsch liquids, and that allows you essentially to look at a facility that will not only destroy PFAS, but will allow you to make a revenue stream depending on what products you're looking at. Next technology is Revive, and there's a gentleman who was speaking better than I on that, and they're based in Columbus, Ohio, and they offer a supercritical water oxidation system that treats contaminated liquids. Char Technologies is a relatively new entry. Basically, they offer a high-temperature pyrolysis system, HTP. They're headquartered in Toronto, Canada, and they treat both solids, contaminated solids, and liquids, and they have a diverse array of feedstocks and products, and as part of their offering, they also provide their systems in a fully fabricated modular form, and I expect them to be more prominent in this business because of their unique attributes. Jadara. Jadara is high-temperature Winkler. For those of you that have been on the planet for quite a few years, you may remember this technology. It's been around for over 40 years over in Germany. It's a bubbling bed, fluid bed, and originally it was owned by ThyssenKrupp. It was purchased recently, within the last couple of years, by a joint venture of GI Dynamics and ARA Partners. They take solid waste only, and they're headquartered in Atlanta, Georgia, and typically their plants are about nominally 1,000 tons a day or larger. ICM, based in Colwich, Kansas, Advanced Gasification Technology, acronym AGT. They have a portfolio of commercial projects that have been operating typically on wastewood or agricultural waste, and essentially they do solid waste conversion, but their operating characteristics suggest that they should be able to destroy PFAS. Their plant size is a little bit lower than many. That's nominally about 250 tons a day of feedstock as their sweet spot. ARTI, based in Des Moines, Iowa. It's essentially a pyrolysis system that was aimed primarily and designed to maximize the production of biochar. And biochar is a very, very popular product now in the marketplace. It has special attributes that are good for the agricultural industry and mostly for home gardeners and so forth. And you'll see that industry grow, I think, in the near term. They have a modular system. It pretty much can fit on a rail car, and they'll deliver it to the site. And again, it's small scale, generally in the range of 5 to 10 tons a day, and they replicate trains in order to match up with larger sizes. In Germany, Spanner RE2 offers a biomass power plant. That's all their units do. They do produce a syngas, but it's of a quality that is only suitable for power generation. Here again, they offer modular units only and solids only. This is a new company that I'm not familiar with, Aquagaga, I believe. Forgive me if I'm not pronouncing it right. They're based in Tacoma, Washington. They offer a hydrothermal alkaline treatment, HALT process. It appears that it's suitable for liquids only, and I don't know much more about them. If they're in the audience here, I'd be more than happy at some point to learn more about you. OnVector, based in Somerville, Massachusetts, offers a plasma vortex technology, which is very, very unique. And the word plasma implies that they're operating at extremely high temperatures and that they're creating a vortex, which suggests they're looking at mixing their materials well. And again, they're focusing only on liquids conversion. Heartland Water Technology, based in Murfreesboro, Tennessee, is essentially their main business is water treatment of all kinds. They have the Heliostorm ultra-high temperature ionic gasifier, and they offer the treatment of both solids and liquids. PyroGenesis, based in Quebec, Canada, offers a plasma resource recovery system, acronym PRRS, and they have a full system from feed prep, gasification, and vitrification, syngas cleaning, and energy generation. And again, they look at handling both solids and liquids. TRS Group in Longview, Washington. It's offer thermal remediation and PFAS removal. And they offer basically treatment of soils and water. By Largo, I think these folks are here at the conference. I haven't met them yet, but they are based in Westminster, California, and are comprised of a group of several clean tech specialty companies. They offer in this arena the aqueous electrostatic concentrator, which can handle, again, both soil and liquids. Lummus Technology, based in Houston, Texas, my old alma mater years ago. They have a large portfolio of process technologies related to the refining and petrochemical business, and recently purchased the Zimpro wet air oxidation technology, which will take wastewater and other liquids and upgrade them accordingly, and it appears that they can handle PFAS as well. This is a fairly recent announcement that came out within the last 2 or 3 weeks. Hofner Energy, headquartered in France, offers a very, very sophisticated system where they use thermolysis and reforming combined to produce a product called hypergas, which essentially is upgraded syngas again. And they can handle only solids, and I'm not sure of their scale, but I'm guessing somewhere in the range of 500 to 1,000 tons a day. And importantly, as you see in this chart, they can make any number of products. And because of their particular operating characteristics, they no doubt can handle PFAS. 374 Water, based in Durham, North Carolina, uses the air supercritical water oxidation process. And again, they were aimed specifically at wastewater treatment, and that includes PFAS. And then finally, just to remind you who we are, we essentially, our main chore in this industry for the last year and a half has been due diligence, and it keeps us very busy, and along the way we learn a lot. I think what distinguishes us is we're very, very granular in what we do, despite the rather simplistic presentation I've made you with regard to these technologies. Don't forget to visit our booth for a chance to win musical DVDs and CDs. Thank you very much for your attention, and greatly appreciate it.
All right, so we are going to save questions till the end. That was a lot of technology, so I'm suspecting there's some questions rolling around in some minds out there. But for our next presenter with Revive is Mr. Trevor Whitson. And so one thing you definitely should know about him is he is a connoisseur and fine Peruvian cuisine cook. So I think it was Ralph and Jorge earlier talking about meeting over Peruvian food. So here's your man if you're looking for some Peruvian tonight. I guess this is where we need to be. So, Mr. Trevor, if you'd like to step up.
Thanks so much, Chef. Yes, sir. Appreciate it. Yeah, I really owe that to my wife. My wife's from Peru, and she's pretty awesome. But along with that package, besides a great wife, I got awesome food. So if you ever look up Gaston Ocurio, he's the Peruvian, is sort of like popularized Peruvian food all over the world here. And some of the best restaurants, in fact, are Peruvian. And there's plenty here in Orlando, so try that out. So I wasn't planning on this part of the presentation, but I certainly would pitch for Peruvian. And thank you, Richard. I think great presentation here about the overall landscape of PFAS destruction technologies. Actually, I told him I'd share with him some of the others that I've seen in the market as well. But the fact is that there's a lot of focus right now on destruction. I think everyone here is feeling pretty overwhelmed by just the size of this problem that we're dealing with, aside from just the cost. And how do we really break the cycle? Whether we're concerned about the environmental impact of the PFAS that's out there, or if we're thinking about liability. How do I know when I've supposedly treated my waste, when is that liability finally done for me? And so we see that's really where PFAS destruction plays a role here. And frankly, that's probably why so many people are putting money into getting into this industry and developing technologies that'll probably each have their place. So I'll speak about just one technology today. So that'll be supercritical water oxidation. And I'm also going to talk about how that technology and many other destruction technologies pair with separation and concentration technologies. In short, these technologies, like supercritical water oxidation, or we call it SQO, they use a lot of energy. Some use more, some use less. And they cost a decent amount, and they usually don't process huge volumes. So how do you make that economical? You separate out the PFAS that you're focused on, concentrate it very heavily, and essentially then you're able to destroy it. In fact, what we find with our system is the more concentrated, the better. It loves those calories. And so we just throw that all in there and get a nice clean water stream coming out. But it's critical to have this treatment train approach. And in fact, that's what Revive, I'll tell you, we're all about. So today I'm going to focus on one, just talking you through SQO, sharing with you how that technology works, how it does PFAS destruction. Importantly, what we've done at Revive is we've been able to commercialize this. So we are fully permitted in facilities. We are actively destroying waste today. And there's a ton of learnings that we get from going through that process. Second, I'll talk to you about the different types of applications that we see. So Richard was exactly right as he described Revive. We're focused on aqueous waste streams, so liquid waste streams. We currently do not handle biosolids, but there's a lot of diversity in the liquids, and I'll share with you our results there. And then lastly, as I said, we've been operating commercially, so there's a lot that we've learned through doing that process, not just about the technology, but about really deploying that technology, whether it's at a client site or in central facilities as part of our model. So Revive Environmental, I was thinking I would have to explain who Battelle is, but it seemed like there's a good amount of talk about Battelle. We are actually a spin-out of Battelle. So Battelle, about 10 years ago, got big into PFAS. They still have many parts of this platform they developed, but one pillar of that platform was destruction. And so once they got those technologies to the point that they were ready to be commercialized, good on Battelle, they said, that's not what we do well. Let's bring in dollars, let's form a separate entity, and have a company that's focused on commercialization. So we were formed at the end of 2022, and in March of 23, we commercialized our first unit. And now we've got 7 units total, and we have 2 facilities. So really a good model. And we have the added benefit of, Steve Rosanski's in the audience, one of my colleagues from Battelle, we get to reach back and use that expertise that was there developing the technology as we try to further advance it. And again, do this in a commercial atmosphere. They said to be patient as you click it.
Is it embedded video?
Nope, no video. Let me see. Boop. There we go. So I won't spend a lot of time teeing up the PFAS issue. The one piece I'd focus on here is just the persistence, right? Again, we keep putting more and more into the environment. It's staying there. We're looking at destruction as a means to try to break part of that cycle. Just to bear with me with these clicks. Okay. There we go. And you hear so much about it, like today, about how overwhelming this is. Wherever you look, you're going to find it. And so this feels like a problem that, almost what's the sense of us addressing this? And if all we're going to do is take PFAS out of water or out of waste and put it somewhere else, it's right to feel like that. But again, this is where we see PFAS destruction playing a role. And we know that the goals we have to get to are really, really daunting. So you've heard plenty of folks walk you through what these requirements are. I'd like to talk you through some of the math. So if we look at something, say, like an AFFF, so a aqueous film forming foam, these firefighting foams, there's a lot of PFAS in there. Very, very high concentrations. You could be in the millions of parts per trillion. And so the math is, how do you go from millions of parts per trillion down to single digits or non-detect? You need a lot of destruction, 6 nines of destruction. And so as you look at technologies and as you look at the applications where you're looking to use them, you do need to ask that question, what is that target that I'm aiming for? But what's my starting position? And so what does that technology need to be able to do to get me where I need to be? And there's another aspect you'll look at there is for which PFAS, right? We've talked about 15,000 different PFAS, and we know which ones are regulated today. So how does it do it for what you're targeting? And, preview, I'll be talking about how SQO actually does achieve that level. So I think Richard gave a really good kind of separation here between incineration and traditional disposal methods where aside from incineration, the traditional methods are really about moving the waste, doing it in a way that we're feeling confident that it's sequestered and it won't get back in the environment, but nonetheless, the liability associated with that waste has simply been moved. And incineration, as you've heard, there are questions out there about how do you run incineration in a way that you are consistently getting the level of destruction that you want and not ending up with PIDs or incomplete destruction, particularly if these are in communities where it gets into the air and has real environmental justice impacts. And so what we're seeing with this new set of destruction technologies, a real focus here on being able to take the waste that you give, characterize it in terms of the PFAS that it has in it, and then at the end of the process, give you analytical data to validate that it's been completely destroyed. It's been completely mineralized. So you want to know, You gave your PFAS to us or someone else, and at the end, your PFAS, and thus the associated environmental impact and the liability, are gone. So supercritical water oxidation. In short, you may have always heard 3 phases of matter. I think there's like 7 really. But we say the 4th state of matter is the supercritical. At very high temperatures, very high pressures, water acts different. And what's important for us in this state is that all the organics that are in that water, including PFAS, are going to be fully dissolved. And as they're fully dissolved, when we introduce our oxygen source, in our case hydrogen peroxide, we're able to actually get that mineralization reaction to take place. And it ends up being pretty simple in terms of what comes out the other end. A lot of clean water. I'll talk to you about how, again, we've deployed this commercially, how we permitted it. Many of our permit standards are drinking water standards. So we process wastewater, and then out we're pushing water that complies with drinking water standards. And then we have salts like sodium fluoride in your toothpaste and water, and then a nominal amount of CO2. That's all that comes from the process, and what I'll share with you is just how complete this is. You may say, well, what about some of the long PFAS? They turn to short, et cetera. The short answer is no. We're doing that for all PFAS, and we're getting that level of up to 6 nines of destruction, so getting us to the non-detect. So when we heard about the EPA's guidance here on destruction, someone said earlier that there wasn't a lot new in it about destruction. There was something new in there. It was a framework for clients and others to really evaluate destruction technologies because there are so many that are out there, it's confusing. And so the EPA laid out these 6 criteria, and we were very happy to see that we had already got all those criteria checked off since we had launched this product. So, are you ready to scale now? We're operating commercially with SQO. What can you process? I said we process different liquids, AFFF, leachate, wastewater. Obviously, having the data analytically to prove that level of destruction. And we all know you can't get 100% mass balance at this point. Analytical doesn't get you there, but every analytical we've done, TOF, AOF, TOP SA, et cetera, all of that is telling us that we're getting the level of destruction that we understand this technology can provide. And as I've said before, broad, so all PFAS, ultra short, short, long chain, and deep destruction on here. So no harmful byproducts, and thus no environmental justice concerns. So we have facilities and communities that, again, are meeting drinking water standards. They're not pushing waste into those communities, or if we deploy on site, there's no impacts to that. And then additionally, we offer, beyond what the framework asks for, is we can tell batch by batch. So today, one of the things that we're involved with is Ohio's firefighting foam take-back program. So we're helping them with a turnkey solution to collect foams from fire departments. We create a registration system for them to put them in. A little bit of data sharing for you that I didn't find on the web, but now I see from our system. We found over 240 different formulas of AFFF. And that doesn't even take into account how maybe a given formula has changed over time with what's in it. So a lot that's out there. But we're doing that program right now where we're taking in these foams, and at the end, what we're going to be able to give the state is, here's the fire departments who we processed this month, here's the materials that we processed for them, here's what the PFAS was going in, and you can see the PFAS is gone going out. So all those fire departments are actually generators of record of this material. They're able to get that verification back that as a result of the program, their liability and that PFAS impact is gone. We give them data that is not just on PFAS, but anything else that they're looking to control for as well. We provide this to the POTWs that we work with. But really, it's all about we treat, we analyze, we verify, and then we discharge. And we provide all that data to our clients. And so our setup here right now in terms of what types of applications is landfill leachate. So very common, we're having a lot of landfills reach out to us, not the ones who are saying, I want to wait and see, but there are other landfills who are being pushed by their POTWs who are saying, you better come up with a plan, you can't send us any more PFAS. They're working with us. Industrial wastewater, there's different companies who, whether intentionally or incidentally, have PFAS in their wastewater or wanting treatment there. AFFF we talked about, and then groundwater is an area we're starting to get into. The big thing to call out here is there's really two modes in which we operate. If we're dealing with a dilute waste stream, and I say these things, I keep saying we, but for a lot of these destruction technologies, there will be a similar paradigm, is when we're dealing with a dilute waste stream, we will concentrate it. So foam fractionation is a popular way to concentrate. GAC is a way to do that. We actually have a technology called GAC Renew we also got from Battelle that pulls PFAS off of the GAC while it's still in the tank, but again, to give something concentrated to put through our system. And then for the foams have so much PFAS you don't need to concentrate it. So that we can throw directly into our system. So it's really dilute waste streams we concentrate, other ones that are not dilute we process directly. And so as I shared, we've been doing this since March of 23. Last year treated 55 million gallons of these different types of liquids. All of that has been verified as meeting discharge requirements when we do that. We've been establishing facilities, so we've now just got one that's gone in Columbus, Ohio. 3 of our PFAS annihilators are there. It's fully permitted with the state, so Ohio's thrilled they can send their foam there and have it destroyed in-state. But as well, we have facility in Michigan, and then as I'll show, we'll plan on having others in other areas. We do deploy these as needed to customer sites. I'll put the caveat that I like you to think mobile, but this is not we're driving to one site this week and next week we're going to another site. If you're going to put it there, you're wanting to think about this being probably months worth of time that it's at a site if you really need it there for a temporary basis. And this is a bit of the setup. Steve and I were talking, we need to update this slide here, but this is kind of our configuration when on the right-hand side, that container is really where the reactor is, so where all the dirty business is done. So dirty water in, clean water out. The left side that we either have in a container or like in our Columbus facility, it's just sort of outside controlling 3 different ones. That's where we control it, so the computer systems. And there's a lot of support in there. What's important to call out is, again, I said we take dirty in, when the clean comes out, we measure that. So in this setup, once the material, the clean water is coming out of that right-hand trailer, the PPC, that's when we're taking our samples to be able to do our analytical validation. But after that point, it goes through some fail stops of GAC and IX for metals. And as well, we have vapor where we hardly get any vapor. We need to put a vacuum on it. We have air permits by exemption, but still we have a vapor GAC on that. So we ensure that nothing is getting into the environment from this, but as well, we're doing that validation every time before we do a discharge. And so we're expanding these to basically have it close to our customers. Many of the folks that we're working with, particularly with these concentration technologies I'll talk about, just don't have enough volume to fill up one of these units. So we look at how do we maybe do it where we can concentrate on their site and then bring to us centrally. But we know there are other customers, other clients who will not want to put their waste on the road. Maybe they have concerns about that, or they do have a large enough recurring need for us to deploy to their site. And so I don't think it was talked about so far today, but foam fractionation, I'm just curious, how many of you know what that is? Raise their hands. Okay, so a good number. So for those who don't, if you used to have fish, thinking about an aquarium and it bubbled up, the bubbles weren't so much about air for the fish, it was actually helping keep it clean. So some of the organics that were in that water would actually stick to the bubbles. So there's a hydrophilic and hydrophobic end, they stick to those bubbles and come up. Fortunately, that's exactly what PFAS do. And so they're able to stick to these bubbles, those bubbles go up, form a foam, and then kind of the keys to it is how do you then take that foam and make it smaller and smaller. So you're able to discharge clean water from this system, but then have a really concentrated waste at the end. I will say this has limitations though. So what we've seen is that with really short or ultra short chain PFAS, they do not stick to the bubbles as easily. There are ways that the different vendors are getting around that. So there's different additives that they can put into there to help with that collection. As well, there's different ways to run parameters on it or other treatment equipment to bring in with that. But if you have a client who has a very high, for instance, PFBS problem, that's something where you may see this provide somewhat of a solution. You may have to look to other technologies to help out. We had a landfill like that. They had a source that was just really providing huge volumes of PFBS, and we couldn't achieve their targets with that. And so the setup of it is really taking leachate in, whether it's on site or at our site, going through this foam fractionation process where we concentrate and separate it. That process itself discharges clean water, and then sending this hyper concentrate over to us for destruction, and usually that's going to be at one of our central facilities. Kind of the way the math works on here is that if you're getting really good levels of concentration, as we've seen with technologies, you could process up to 5 million gallons per day of landfill leachate because you can just really concentrate it so much, and our capacity of our unit is 500 gallons per day. So sounds small, except when you're pairing it with these technologies, makes it very economical and efficient. And so some real data. On here is destruction from the landfill leachate. On the left is different short chain PFAS. On the right, different long chain PFAS. And if there's any that you're looking for up here and you don't see, send me an email and I'll show you, but the answer is the same. We get them down to non-detect. And so you'll see there's a blue bar and an orange bar. You don't see orange bars unless you're really close up there, because essentially that's saying that the clean tote, it's non-detect for all of these analytes. And when I show you more about AFFF, the firefighting foams, you'll see very similar results. So there was a little bit of discussion today about that transition to fluorine-free. I tell you, that's probably where a lot of our business is coming from today. So we certainly have a lot of landfills and industrial customers, but it's really been a lot of airports and states who are saying, we want to get out of this stuff, let's transition. Not everybody's ready to do that, but I tell you, there's been a very strong demand to do so. And as they're thinking about that transition, a huge part of it is, what do I do with my waste? Whether the waste is the AFFF that's still in my closet, if it's the rinse water that I do by cleaning out my system, or maybe it's an entire system. You know, maybe I want to just start new and throw this one away. So they have to really keep that in mind to be able to be efficient. And so what we've seen is either we're getting something very concentrated, like these foams, and for us that's very straightforward. We just put it through our annihilator, destroy it. We actually have t-shirts that say, I love annihilating AFFF, because it almost like works like a lubricant almost for the machines, very good. But then we have these dilute waste streams as well, where it's really that same idea. We just want to concentrate them, foam frac or something else, and get a concentrated waste stream to go in. And so this is a picture that we have. We showed this at a media event for the Ohio EPA as the governor kicked off that. And so really was trying to show here is on the left, that table, what were the EPA's targets, what were Ohio's targets, and then showing what our starting point was in the AFFF before we go through destruction and then after. And so you can see in that third column, effluent after destruction, we're well below all the targets that they have. And then it's not just those 6, it's all the PFAS that are in there. And so you can see even something like we talked earlier today about 6,2-FTS, right? Very prevalent, very mobile. 188 million parts per trillion. So again, remember 6 nines of destruction, what does that get you? And that's what's helping us get down to such an incredibly low level here. And as Richard mentioned, temperature is a big part of that. As we run our systems, we see kind of the hotter we turn it up, more so than the pressure, the hotter we turn it up, the more destruction that we get. This is a mobile deployment at a DoD base. And so really, lessons learned here. I mean, first and foremost, we as Revive, we're a company that operates these units as a service. So we don't sell units and tell clients, here's how you need to learn how to use this, et cetera. And there are some destruction technologies that do that. Ours is about a service. So we say, you've got waste. We're going to be able to take your waste and come back to you with data to show you. So as we do that, safety is obviously paramount, especially if we're on a client site, but as well at ours. And so we lead with that, but as well, we've also had a lot of transparency, particularly with regulators. As I shared, we're oftentimes trying to meet drinking water standards for wastewater. And the way we do that is in partnering with the regulators to say, hey, they don't have a standard in place. We show them what our system can do, and we help them draft essentially what that standard will be for us. And for instance, when we first did that in Michigan, they had none, so we just simply copied and pasted the standard that they had for drinking water. And of course, we're providing data consistently to show them that we're continuing that compliance. Secondly, people have asked, I was talking with some of my friends from Bologna, and they were saying, hey, don't you guys just kind of have a nice price sheet that can tell us, like, if the waste is this type, here's how much it costs. If it's this type, here's how much. That is great. That's somewhere we like to get to. We are not there. So I feel very good about where we are on the journey of processing things commercially, but what we're really learning is every waste is different. I told you AFFF, 240 different flavors. And so you can think, well, aren't they all similar? Yes, somewhat similar in the PFAS that they have, but they have a whole bunch of other stuff in there, a whole bunch of other organics that we need to consider. And then landfill leachate, shoots variable day to day, right? So a lot of variability there. So for us, it's been key that every time we're engaging, we're having to really look at what is in that particular waste and what are we trying to achieve with it. We do not have a formula yet to say this is good, this is bad, or a red flag, but we're working on it. One of the things we look for is salts. So he didn't talk about this before with Richard, but each of these technologies does have limitations or weak areas. One for supercritical water oxidation is just salts. It can plug up the system just because of the temperatures we're working at. We're very much able to manage that. We've developed a lot of know-how and IP around that, but it's something that we want to know what's coming in so that we can prepare for what's going to essentially affect our system. And then lastly, I would share is not all the challenges that we're facing here are technology challenges. They're not about, does SQO work? Do we get destruction? Sometimes it's, if we're going to a client site, who's the subcontractor we're working with? What are some of those dependencies we have on them? When we transport a unit, are there things that maybe get jostled in the unit, and so when it ultimately gets to the site, it doesn't operate like it's supposed to? So we're working through those things, and again, that's why we're very happy about being commercials. Those are kind of things you get to experience as you're doing that. We're building a recipe book, and we're finding out how to best operate in different situations. So hopefully I've been able to share with you, a specific PFAS destruction technology that is ready today and how that matches up with technologies. Again, I would say for any of the destruction technologies you're looking at is try to figure out what is it that makes that technology most economical. For many of them, it probably will be concentrating. And then, really how we've learned in running this, aside, we're not doing pilots, we're not doing trials, we are doing commercially, seeing that so many wastes are different, and that really does have an impact on what we can do. And so we're very much having to learn as we go through each one, how can we efficiently destroy, and then how can we achieve the results that our client wants. Thank you.
All right, thank you, Trevor. So it's a little mind-boggling that in a few years we went from like parts per billion to parts per trillion, and we're like, oh, 6 orders of magnitude reduction, no problem, we got this. It's kind of blowing my mind, but our next presenter is a former colleague of mine at REGENESIS, and I didn't even have to ask this fun fact. So she is quite the equestrian. She learned how to ride as an adult and competes now some, right? And wins some, maybe? Once in a while? Okay, once in a while. So Maureen Dooley is going to take us from the surface to the subsurface.
Great, thanks. Hi, how's everybody doing? We're getting there. We're so close. We're so close to happy hour. But yes, I had the opportunity to work with Chad for a number of years. Fantastic person, fantastic scientist, person, presenter. So anyway, I appreciate it. Thank you, Chad. So, PFAS, remediation. One thing I found really interesting today is that we've had this thread of airports kind of running through the entire presentation. We had, like say, AFFF transitions, talking about liability, talking about funding, getting into forensics, really interesting data analysis, and I think our friends at the airports have some, issues that they need to deal with, and they are being proactive. And what I want to talk about today are a few sites where some of these airports or airfields are being extra proactive because they had drivers that were moving them to get into a remediation scenario maybe a bit sooner than some of the other folks or other facilities that might be out there. So I'm just going to jump right into groundwater remediation, and honestly, there's really only two options. Okay, so we're talking about destructive technologies, but really what the remediation options are groundwater extraction or an in situ stabilization. There, unfortunately, are no in situ destructive options available, at least yet. So talking at least initially about groundwater extraction, pump and treat. So what's required is you're going to, pump the water out of the ground, and now you need to manage the groundwater and PFAS or PFAS and other contaminants that may be present and manage that waste. So things to consider when you're looking at, a groundwater extraction system. These are systems that you're going to need to likely operate for a while. What are the scenarios that I'm talking about? So the particular cases that we've looked at and we look at quite often is that you may have a site situation where the objective is to stop PFAS from migrating off-site. So there's a sensitive receptor. It could be an eco-receptor. It could be drinking water wells, and that's really the critical component. So at this point, so you're really setting up an engineered control. So for the groundwater extraction system, you're going to need to run this for a particularly long time, and I think it's important for you to understand that during this time, you're going to need to manage, any waste that's generated. Things to consider, where you set those extraction wells, are you going to be drawing contamination downward? A lot of times your PFAS source may be up in some of the upper levels, so you start drawing that down, or towards the extraction wells, you may be expanding some of the zones where there's contamination. So these are just things to consider, and and also just as a final note on that is that we were doing a lot of groundwater extraction in the days, with Superfund sites, and many of these sites are still operating because they haven't been able to achieve, these 5 part per billion standards. And so now we're looking, as Chad mentioned, at part per trillion standards. So if, the idea of a groundwater extraction system cleaning up the site, you still, 30 years later, are going to have a considerable amount of PFAS still remaining. So just a point on that, and I'm going to move on to the stabilization, but an really interesting paper was recently published that you might want to take a look at, and it's just looking at the whole idea of pump and treat. What are your objectives? What are you trying to achieve? And as was stated, earlier, there are a lot of tools. We need tools, and so there are tools for everything, and not one size fits all, but just things to consider if you're looking at, some of those options. So what I'm going to talk about is, the methodology used to stabilize PFAS in situ to address groundwater. So what we're using is a colloidal activated carbon. So you take activated carbon, you mill that down to 1 to 2 microns. It's then suspended in a polymer that allows this colloidal activated carbon to be injected under low pressure and get distribution. We're not going to have any hydraulic changes. And we have actually 2 formulations now. We have a liquid and a solid. So it's a source stop and plume stop. So how is the remediation achieved? And I know there's a question, and I'm going to get to that, like where is it and what's happening and how long? But what we're doing is you're going to have these colloidal activated carbon particles coating the soil. So we're creating this carbon filter underground. So that's the objective. So as groundwater with PFAS moves through this particular zone, the PFAS is going to sorb onto this colloidal carbon, and then you have, your clean water moving to the other side. I mean, it's simple, really. And the challenge, honestly, is just ensuring that you have the distribution and you get this colloidal carbon where it needs to be, and that you have sufficient quantities to manage what's coming in to your system or into your barrier, looking at a barrier design. People talk about remediation, and we like to sometimes point this out from ITRC, it doesn't necessarily have to be a destructive technology. What we're really doing in a remediation is we're managing a risk. We're eliminating an exposure pathway. So if you for instance, chromium is stabilized, we don't remove the chromium from the ground. We're able to create a situation where you don't have hexchrome anymore, and you're able to manage that risk and manage that exposure. And so that's really what we're doing here as well. So getting to airports and some of the results and some of the information, and the big question is, how long does it last? I mean, really, what's our design? What are we trying to do? So no, we're not destroying it, but we're changing the equilibrium of the subsurface. So the flow of the PFAS changes substantially. So you're creating, it was I think mentioned in one of the earlier talks, is really the stabilized zone. So your levels in groundwater, so PFAS in groundwater is removed, and so levels are significantly less, and you can get down to these very low part per trillion levels. So as far as like how long does it last, this is going to depend on what your flux is, how much contamination there is there anything else that happens to be present? Because we're pretty familiar with isotherms, and we know how much sorbs and what the behavior is. So you're able to model this, and in the paper that's shown here is they looked at 17 different sites and looking at how they had actually mixed contamination, so PHCs, chlorinated solvents, along with PFAS, and we're able to document the performance. And what I think some of the biggest takeaways from that were that you can get decades of longevity, I mean like 60, 70, 60 years. But I think another important point is if you're at an airport, for instance, and you have a point source that is, maybe where a fire training area is, and you're able to stabilize that or remove it or address that source, that also you have less coming into that barrier, and that it can quite often give you the opportunity to just have a one-time application to address and stabilize that plume. So this is an option, that's available, for some of these situations, particularly when you're looking to mitigate something very quickly. And just looking at a snapshot of some of the results we've had, and then keeping in mind like plume stock or colloidal activated carbon, we've worked with that for almost 10 years now, so we have a lot of experience with it. And then getting back into with PFAS, I mean, we actually had some of our first sites, going back almost 7 years now, 7, 8 years. So we've learned a lot with this experience. But anyway, looking at this snapshot here of some of the different sites that we've had, and these are specific to airport sites, we've been able to, meet remediation goals. Some of these were the 70 part per trillion, but there's a bit of a range. But we're definitely at least below 70, in some cases below 20 or below 4 parts per trillion, for each of these sites. So the ability to get a rapid response, has been shown, quite frequently. So I'm going to get into some of the details, and how you get into a design, some project results. Now, the Grayling site is one that we show a bit, but the reason I want to present this is to just walk through the process and what's involved in a particular site and some of the things that you're looking at and important characteristics. So this was actually a pilot test. The site itself has, coarse, fine, medium grain sand, so it's got some transmissivity. You can see the levels of PCE and PFAS, 130 nanograms per liter, plus about 8 parts per billion of PCE. And the driver on this was a pilot test, but this is looking to protect an ecoreceptor that was on site. So when we get started with a project, what are some of the things that we're looking at? We need to really understand what's the contaminant mass. We need to understand the flux. And we also need to understand the vertical distribution. Quite often you can have a 1 or 2 foot zone where most of your groundwater flow is running through. So understanding that allows us to fine tune our design to ensure that we're getting the capture that's required. Non-target compounds, TOC, And that's why sometimes a site like a landfill might not be appropriate because there's just too much other, too many other competing contaminants or TOC, and it might not be appropriate for PFAS. So what we're going to look at carbon dose, vertical, and what's the time, what's the barrier time length that we expect that this to be remain, viable for. So just a simple layout. How is this applied? It's applied through direct push. The numbers, there 1 through 9 were just the injection points, usually spaced anywhere from 5 to 8 feet apart, depending on the particular site. So it's just in direct push. Please note the pressure, it's just 16 psi, so this is a low pressure injection. And again, it's really critical to make sure that we're getting the delivery and distribution. So, and well, I'm just going back, there were two down gradient wells, and I'll come back to that in a bit. Yeah, you see the 2 down gradient wells at 6 feet and 10 feet. Something else that's really important that we've incorporated in all the field applications is this placement validation. So we're going to deploy, or excuse me, collect groundwater, collect cores, soil cores, and along with putting in some piezometers so we can look for evidence of the colloidal carbon, which is a black color. So for this, and this just shows an example of where we look at that. So what we're looking for is that distribution over our target zone. So in the first picture, you see just the native material. The second picture shows where we were getting some distribution, but we weren't covering the entire area, made some adjustments, and then we were able to cover the entire vertical zone. So looking at results. So this is just showing really the first 6 months, and the blue line designates the upgradient wells, and then you see the immediate reduction in these wells that are like 6 to 10 feet away, meeting our targets. Oops, sorry, so I'll go back. And then the last one, I can go back here. This is showing the PCE, and that was having the same results that we observed with the PFAS compounds. So at 6 months, they decided to install 2 additional wells down gradient to be able to monitor, at 26 feet and 45 feet to see what sort of reductions were being observed. And they also saw that the groundwater flow was actually in a little bit of a different direction, which happens sometimes. And so the results here, you see, again, that even in the down gradient wells, when we average all of these wells, that everything was down below reporting limits. So you had the new wells installed, and we actually are down to 10 nanograms and 2 nanograms per liter of the PFAS compounds. And seeing, similar results, again, with the PCE. A question that comes up sometimes, what about hydraulic conductivity? The colloidal carbon is really only about a 10 micron coating over the soil particles, so this just shows some slug tests before and after and no measurable change. And so much source stop, so at Grayling itself, we're also looked at some soil stabilization. So for this particular site, what we applied, I just want to show just a new formulation that we have. We have the source stop. This is meant for vadose, capillary fringe type applications where things are in higher concentrations. So we have the solid form and the liquid. The solid is actually a combination of colloidal activated carbon and GAC. And I don't show the video, but what happens is once it's hydrated, the colloidal carbon dissociates, so it allows it to move and almost, can get into some of the finer grain material. And what that beakers show is 1% GAC versus 1% of the source stop. So if you're considering stabilization in those situations, we're looking at reducing leaching. It's not direct exposure, but just reducing leaching to be protective of groundwater. It's likely that you would use less material. So for this particular case, we've got, 84 cubic yards. We've applied the source stop. In this case, it was actually the liquid. And just, jumping ahead, you can see the results. Immediately after post-treatment, you were able to, the SPLP analysis, and then 6 months later, all the PFAS were non-detect. But I just want to jump in quickly to a couple other sites. So we have the Martha's Vineyard Airport. So at this particular site, this is one of these cases they kind of can't wait. They needed to kind of move it along because they were concerned about groundwater that was moving off site that had the potential to impact residents. Now, when you're on a place like Martha's Vineyard, I think you're familiar with it, it's an island. They do not want to have to manage a lot of waste. They don't want to ship things off the island. It's extremely expensive. So it was really important to be able to keep things on site and manage their liability. So in this case, our goal is the sum of a Massachusetts 6, so 20 nanograms per liter. And it was this is, an initial phase right down gradient of a fire training area. We had a 60-foot barrier, and just looking at the results. So we're almost about a year out. If you look at the upper box, you can see the red line, that's where the barrier is. Typically, we're gonna have a well that's at the barrier or very near the barrier, so we understand what's happening, because sometimes if you've had that horse that got out of the barn and you have variable sites or soils, you might have differences in, the response time. So that gives us a real indication of the barrier. So anyway, the results that I'm showing here is that the well that was 5 feet from the barrier itself was non-detect after 3 months. And then the next well, which was 25 feet down gradient, you can see how the PFAS levels dropped in the last reading that was at 5 parts per trillion for the combined 5 compounds. And so the plan at this site is to move ahead with actually a little bit of soil stabilization. They've got a little bit of some source material, and then the expansion of the barrier. And then just one last site. Again, it's a similar situation. This is a site in Michigan. This is a silty sand, so not quite as transmissive of some of the other sites that we looked at. And so this is part of the pilot program that was taking place in Michigan, and this was, so it's a pilot test. And just jumping ahead, this is where the location where we're looking at some of the key wells. And so for this particular site, this is where we injected the colloidal activated carbon just within that vertical zone, even though contamination is found to be deeper. And so then we saw, very rapid and, maintained reduction of the PFAS contamination. And so what they're waiting for is additional funding to come through, hopefully with the state of Michigan, because they have some remediation funding set aside. Okay, we'll talk about cost. This is one site. Now, this is a really small one, so 73,000, but it was 73,000, and this is about 7 years in going. And compared to a groundwater extraction with GAC would have been about 1.3 million. Much larger project. This is a full-scale operation that was in Michigan. So the plume stop installation was about 3.5 million. This was, at least 2,000 or 2,500 feet of barrier. And the estimated cost there, if you were going to have a pump and treat system sheet pile, was about 20 million. So you can get a sense of what the cost differential is. So what we're doing, we've got ongoing research. We're part of CERDEP. We've got a couple sites here in Florida. We're NAS JAX. We're part of the CERDEP demonstration. And there's another location that we've been on, another airfield in Florida as well. So with that, I'd be happy to take questions later. Thank you very much.
All right, our fourth and final speaker, Mr. James Erario. I actually stalked his LinkedIn profile to get this fun fact, but he spent a few months in Bolivia putting in and installing freshwater wells. So if you guys know me, it's kind of near and dear to my heart, so I thought that was pretty cool. So without further ado, Mr. James.
All right, hello everybody. My name is James. I'm a project engineer with TRS Group, and I'm going to talk to you about another tool in the toolkit for treating PFAS in soils. So we'll start with a little definition and description of what thermal treatment is. We'll talk about a couple of our job sites that we have completed, and then we'll end with a little bit of info on site selection and sustainability. So in thermal remediation, TRS will come in and we will install heating infrastructure in the target treatment volume. And that heating infrastructure will heat up the soil, the groundwater, and the contaminants. And it will volatilize some water and contaminants. And those vapors are drawn to the surface where we treat those with different technologies. And for PFAS, we're using carbon currently. Our sites are run with grid utility electricity. So both our heating elements and also our water and vapor treatment are run through grid electricity. So at TRS, we've been performing thermal remediations for 24 years. We can treat a variety of contaminants, and we have several different technologies and methods to treat those. You can see on the bottom some of our contaminants that we treat. PFAS is on the higher end of our target treatment temperatures. And for us, that means we're going to be using thermal conduction heating technology. So that is what I will focus on today. So what does high temperature mean? We went out in 2019 and we performed a bench test study to see at what temperature we're able to remove PFAS from soil. And I'll stop here. One of the things that has been said is that there is no thermal destruction of PFAS in situ, and that is correct. That is not what we are doing. We are desorbing that PFAS from the soil so that we can draw it to the surface and concentrate it there. So about 350 or 400 degrees Celsius is where we're seeing really great reductions of PFAS in the soil. So we're able to use this information from our bench test studies to inform our temperatures at some of the sites that we've done. The two sites we've completed are ESTCP sites, one up in Fairbanks, Alaska, and one just south of Sacramento, California. The picture here is from Anchorage, Alaska, where we have a site that is just starting up, and I will give a little preview of that in a little bit. So at Eielson Air Force Base in Fairbanks, Alaska, we had a small ex situ pile that was already in place. We actually did not manipulate this pile. We treated it in place. Some moderate concentrations of 62 micrograms per kilograms of PFOS to start. So this is a site plan of one of our job sites. The things to note are in red, we have our array of heaters. There are 48 on this site. In purple, we have our soil vapor recovery points. That's where we're gathering up those vapors. And then in green, we have our temperature monitoring points. So two things about those temperature monitoring points. The first is that we are going to install those temperature monitoring points at the coolest part of the soil. They're going to be the last to heat up and the last soil to be treated so that we know that all of the soil in our piles are well treated. The other thing is at each point where we have a temperature sensor, we're also doing our baseline and post-soil samples so that we can compare the temperatures that we achieve to our reductions in PFAS. So this is a little video that gives kind of a good three-dimensional understanding of what we're doing. 48 of those casings are going to hold our heaters, and inside those heaters are specific alloys of heating wire that function just like your toaster does. So those red wires in your toaster and our heaters have electricity run through them where they heat up. And the heat from our heaters will radiate out to these casings, and it will continue to conduct out into the soil until those heat fronts connect at the coolest points where our temperature sensors are. As we continue construction, one of the most important parts of our build is high temperature insulation. So 300, 400 degrees Celsius is very hot. We have a specific type of rock wool insulation that we use for our sites. And that's going to reduce the amount of energy that we need to input in the soil, reduce our resource load. And it's also going to make sure that every bit of soil reaches temperature. So to protect this important insulation, we'll put at least one layer of liner on top to keep it dry and make sure that stays functional. So here's a completed site. You can see on the back right, we have a tent also over that treatment pile that's going to help protect it from the elements. You can see we treated into the winter here in Alaska, and we use that to also allow us to have a working area around our pile. In the front here, you'll see some of our power distribution equipment. The switchgear is connected to the utility power from the base, and our power control unit allows us to direct electrical energy to certain parts of the pile as needed. So this is a summary of the surface treatment that we have for our PFAS, and it's broken into 2 or 3 parts. On the left is the vapor recovery wells that are coming from the pile. On the top, we have our vapor treatment, and on the bottom, we have our liquid treatment. And the things in the middle are going to help separate those vapors and liquids so that we can treat them separately. The first thing that the very hot vapors enter when they leave the pile is a wet scrubber, where the hot vapors will go up through the scrubber while processed water will rain down. That will help cool the vapors and also, as much as we can, take PFAS from the vapor phase and bring it into the liquid phase, which is beneficial to reduce the amount of solid waste that we have at the end of our project. Those vapors will continue up to a condenser, where a cooling unit in conjunction with the condenser are going to dry that vapor out further. The vapors will continue to vapor carbon, where they're treated and discharged. And then the liquids that are pulled from that will join the scrubber liquids and continue through our liquid treatment system. We are currently using carbon for these systems, but they're plug and play. So we're really excited about some of the new technologies here and would be excited to partner with teams and have destructive technologies to completely remove our solid waste at the end of projects. So we operated into December up in Fairbanks, Alaska. A fun fact, because I wasn't there, was that we had the lowest temperatures ever on site of negative 40 degrees Celsius. That was the temperature in Fairbanks. At the same time, we reached the highest soil temperature we'd ever done at TRS of 400 degrees Celsius. So even in the coolest temperatures, we're able to reach target temperatures. We'd much prefer to do it here in Florida, but that's what we were working with. We built an equipment tent to manage some freezing. We were able to barely keep it above 35 degrees Fahrenheit, and along with some resistive heating wire, we were able to operate into December. So when we started our project, we had one main goal with the STCP, and that was to reach our target temperature of 350 Celsius for 10 days. And at the same time, we wanted to gather data. So we were able to get pre and post treatment soil sample data for PFAS, and also measure our vapor influent and effluent along with our liquid influent and effluent to ensure our systems were discharging appropriate levels. So this was one of the first thermal models we created for a PFAS TCH site. On the left, we have the modeled energy, there's temperature on there, heat losses, and the same as the data on the right. And one thing I want to bring our attention to is the red line. So that's our temperature modeled on the left and actual on the right. And although we were a little delayed, we did reach that target temperature of an average of a little over 400 degrees Celsius. In blue, we had our energy usage, the total energy we used from the utility. We were very close on that. And in gray were our heat losses. So for our first go, we were really happy with the data that we were able to model before we got to the site. So this is a blow up of that right side. It's our actual soil temperatures. And it's kind of got an interesting shape to it. And there's 2 reasons for that. When we go to a job site and we're treating for PFAS, we will start our heaters. They'll heat the soil up, heat the groundwater up, or soil moisture up very well, and we'll reach 100 degrees Celsius. Once we reach 100 degrees Celsius, all of that energy we're putting into the soil is actually going towards boiling off the water, because we cannot get over 100 degrees Celsius until all of that water is gone. Another issue that we had on this site, a real world issue, was we had a power outage for several days on the site, caused a couple issues with our heaters, so that was another great lesson learned that we were able to draw from this project. Once we're able to remove all of that water, we kind of have rapid heat up all the way to our target temperatures. So let's look at some data. We have data for PFOS. In red is our pre-concentrations and in blue is our post. So we had really great reductions, PFOS down to 4.1 micrograms per kilogram. PFOA was non-detect. But there's one piece of data that was the most helpful for us on this project, and that was at E3, which is 5 from the left here. You can see we didn't have the reductions we were looking for. And that coincidentally was the only location, the only temperature sensor that did not reach our target of 350 degrees for 10 days. And that information is invaluable to us because of a couple of reasons. The main one, though, is we know that we are targeting the right temperature. We are not using excess energy. We are not being wasteful. We're being very efficient in how we're operating our sites. So we were really happy to be able to gather that data here. So our ex-situ project in Eielson told us we could get significant PFAS reductions when we were able to reach temperature down to non-detect or near. We were able to achieve our surface water discharge criteria, and then had that one lesson learned about electricity source and making sure that was reliable. So we'll talk a little bit about our in-situ soil project at Beale Air Force Base, which is just south of Sacramento, California. Chosen for its dry climate and the fact that the site was fully in the vadose zone. When we are treating in situ, we are not able to treat in the saturated zone. Vadose zone is where we can avoid having to heat up all of that water that's in the saturated zone. Our technology is not the best for that. Much higher concentrations here at Beale, up to over 1,000 micrograms per kilogram at some of the hot spots. The equipment that we use for in situ is virtually the same as ex situ. A lot of this equipment was actually brought down from Fairbanks, Alaska directly to Beale Air Force Base to be used. One difference that we do have here is a different type of insulation. Here we have an aerated concrete. And aerated concrete is great because we're able to pour it, cast it. The air in the concrete is a great insulator. And we have a nice solid platform upon which we can work and sample. One other thing I'll point out here is our scrubber, which is towering in the middle of the job site. That's that first bit of equipment the hot vapors will hit, where it will go up that while the process water will come down. So for Beale data, this was a great graphic created by Jacobs. It shows total PFAS concentrations in the shaded colors, and the rods show the temperature of our temperature sensors. So on the left in the pretreatment, all of the rods are green, they're cool, and on the right, most of the rods are red. You can see on the left side of the right plot in our post-treatment, where the rods are red, we had great reductions to at or near non-detection limits. Where we did have some concerns were on the right side. We had some temperature sensors that did not reach temperature, and we actually had one of the rainiest seasons on record in Sacramento. So surface water was affecting our temperatures by getting into our treatment volume, and all that energy required to boil off that water kept us cooler than we were hoping to be. And you can see that represented in our data. You can see, over very high input concentrations on some of these soil samples down to very, very low levels of concentration. PFOA, 0.07 micrograms per kilogram, and PFOS, 1.75, specifically where we were able to reach 350 degrees for 7 days. Even at the zones where we didn't reach our target temperatures, we still had reductions, but something a lesson learned for us. So yep, like I said on the bottom here, water infiltration was a big lesson learned. In the future, we can install things like surface drains. We can pave the site to manage surface water infiltration. But we also had very good reductions where we reached target temperatures and also reached all of our surface water criteria. So this is Anchorage, Alaska. I was just on this site last week, and we are currently ready to go, waiting for a couple last approvals. Much larger site, 2,000 cubic yards. You can see this tent is a reusable tent built on shipping containers. So we can move this around to different locations to treat PFAS soil on site and avoid having to transport it. So excited to talk about this, the results from this project soon. So a little bit on site selection. Here in Florida, you're likely going to want to do ex situ just because of the shallow water table. Ex situ is going to be better for soil that you can easily excavate and things that are shallower. In other locations, in situ is going to be good at treating deeper impacts, but it is only good for the vadose zone. Insulation is needed for both methods of treatment, and our ex situ is going to use horizontal heaters, which allows us to use less material. You can see them just sticking out at the end of this pile. These heaters are about 100 feet long, and it allows us to have less heaters, use less infrastructure to get the same performance. If we have to treat PFAS-impacted soils, and we want to actually remove maybe a source zone or remove the PFAS from the soil, there are some benefits to using thermal remediation. We're continuing to reuse our equipment on multiple sites, excited to reuse our materials. The amount of impacted material at the end of our treatments is very low, like some folks were talking about before, taking a very large amount of contaminated PFAS soil and currently bringing into a very small amount of impacted carbon that can be managed. It reduces the need or eliminates the need for soil landfilling, so there's no need to transport soils via mostly fossil fuel driven vehicles, if you can even find somewhere to landfill your soil. Additionally, we only use grid electricity, which currently has green energy as part of that portfolio and is only getting greener. So as treatment technology using electricity, we're positioned well for a green grid future. And then compared to the incineration and landfilling, we're able to use less greenhouse gases for those reasons. So thank you for listening. I hope that you come over to our booth if you have any more questions. Thank you.
So clearly James does not realize that we already reached 400C in Florida, and there's no need for thermal conduction here. So, but besides that, these guys are really in a rush to get to happy hour, team treatment here, but they got about 30 minutes. So let's not make it too easy on them. I know you guys are probably in a rush for happy hour too, but I know you've been holding some of those questions, so please fire away. Just to warn you, I have 30 minutes worth of questions in front of me. You don't want me to ask mine, so.
The bar will not open unless we have 3 questions.
Hi, I have a question for Trevor. This is Lauren March with Arcadis. You mentioned that SQO has some sensitivity to salts, and you've developed some IP that manages that problem. So I was wondering if you could expand on what that IP looks like and what approximate salt content that allows you to accept as far as feedstock wastes.
Yeah, it's a great question. So I won't be able to expand a lot on it because some of it is know-how, is not protected. But I mean, really this is about understanding what are those different salts that we have and at what different points salts would drop out. And so we look at different technologies either to remove salts or we look at how things go through our system to be able to drop them out in a way that is controllable and maintainable by us to be able to get continuous operation. In terms of how much is too much, it really depends. So there are things, for instance, like silica, we really don't like. So there are some salts that are more problematic than others. And so this again gets back to my point about every waste stream we take a look at. It's really why we start out with a project evaluation form, say, tell us all about your waste, so we can really see those different parameters, see what red flags might be. And then we'll typically do an operational demo for folks. So we'll run material through one of our commercial units to be able to actually see how we kind of turn the knobs, pull the levers. Oh, sounds like the mic went. Oh, there you go. How we do that to be able to efficiently run the material. So case-by-case basis, I don't have strict numbers to give you on it. Sure.
This question is for Maureen. Over here. Oh, such a big audience. Well, great panel, but my question's for Maureen. And in the results slide that you showed, I saw a note about plume shield warranty, and I was just curious what kind of warranties, guarantees is REGENESIS offering with some of the stop products?
No, that's a great question. So we do offer a warranty. It can be anywhere from, I think, 15 to 30 years, where we'll maintain the barrier. So if something, if we see something where there's an area where it hasn't been maintained, we'll come back and fix it. So it's, in essence, that's what that is. And we do have a couple sites that are working under that warranty right now.
This question is for Trevor. Great panel, by the way. You all did great. For the supercritical water oxidation, I was curious. You had 4 or 5 units, right, that are up and running?
7 units.
How many?
7?
7?
Mm-hmm.
What's the range in GPM that you're operating those, or gallons per day? And is there a cost range per gallon that you can kind of give us an idea? And does it change based on the concentration of PFAS compound?
Yes, so 2 things. So 1, all 7 of those units are essentially the same, and so their capacities are the same. We haven't yet branched out to have smaller or much larger capacity units. So even our Columbus facility, we took 3 of our mobile units and just put those side to side. In the future, maybe we build a much larger single unit that can handle that. So the capacity we're seeing right now is up to 500 gallons per day. So that's, again, where it gets back to separation concentration, because that's not a lot unless what you're able to do is take a very high volume and concentrate that. And then from a cost perspective, again, that gets back to what I was sharing with Laura there. It really depends on that particular waste and how we're going to operate with that waste. So AFFF is one that we tend to have a little bit more consistent pricing, and I can provide that offline. But when we look at leachates and wastewater, it just really depends what's in there, where are we starting from, and what do we need to achieve.
I actually had a question about the in-situ electrical heating. How come you do that vertically and not horizontally?
If I understood your question correctly, our in-situ systems are built vertically for ease of installation. So when we're installing from the top, we can use a standard drill rig to install those. But when we're using or creating an ex-situ pile, we're able to manipulate the soil how we'd like. And using those longer heaters allows us to just do a more effective treatment. Yeah. Mm-hmm. Yeah, in situ would be vertical and ex situ would be horizontal.
Cool. I think this is a question more for Trevor, because I know for the service that you guys are providing, you're very specific in saying that we're not selling the equipment, we're providing more of a service. Mm-hmm. I know in certain industries, I can see PFAS right now that there's a lot more conversation around it, and with more conversation, I would imagine there will be more demand for the equipment that you guys are providing. With that being said, do you guys believe that the services that you guys provide will keep up with the demand that you guys see for PFAS destruction in the future, if that makes sense?
Sure, it does. Short answer is no. This is a very big industry, and there's a lot of technologies that'll need to step up to really be able to handle the capacity of demand that's there. As it is, for instance, this Ohio program, Ohio had estimated they had 30,000 gallons of AFFF. So far with our registration system, they've had about 30% of the fire departments who are eligible to register. We're at 70,000 gallons. And so it's just, how much material is really out there that we need to destroy. We'll kind of see. We're going to do our best. We'll build more equipment as we're seeing that demand go up. And then from a services perspective, I mean, our view on this is that, one, it's a great way for us to make sure that we can guarantee results for our clients and we can bring together multiple technologies, whether they're ours or someone else's, to deliver a result. We think turnkey is the way to go. But as well, we know that there's tons of uncertainty. As we said before, the fear of the unknown. The unknown is like, where are the regulations going? And so does someone want to make a very big capital investment, then get their team trained up in the infrastructure for something that might be a moving target? We're providing results, and we can adapt the technology as needed to continue to provide those as the regulations change, not requiring our clients to do so.
Thank you.
Yeah, I was wondering, with the thermal heating, is it better for, was your experience better for in situ or ex situ? Which was cheaper?
When we look at
Ex situ or in situ?
Yeah, when we look at the pricing, generally larger is better. So some of these sites, they're very small, they're great demonstrations for us. But when we can treat larger amounts of soil, we can have better pricing for those. And it really depends if it's an excavatable soil. If it's shallow and wide, then ex situ is going to be the way to go. But if you have deep soils in the vadose zone, then you're going to want to go in situ.
My question is also for James. What factors do you consider when you determine the length of time to do the testing? So I know some of your case studies you had mentioned like 10 days at 350 degrees C. What site-specific factors do y'all consider when determining that?
Sure. When we are designing the thermal models for our site, we are targeting efficiency. We know that we need to reach 350 degrees C, maybe 400. We could have installed 100 heaters in Eielson, and we would have reached temperature faster, but we would have spent more building those heaters than we would have saved in the time saved. So we're able to balance the amount of time that we're on site, which is generally about an operation time of about 4 months, give or take, with the amount of infrastructure that we need to build during construction. So we're balancing those two factors.
Sorry, follow-up question.
Mm-hmm.
Does the concentration in the soil or the properties of the soil, whether it's sand or clay, does that play into the model and affect the timing?
Yes, yeah. The most important factor is soil moisture content because we have to remove all of that moisture. And then concentrations as well are going to play a factor, but the main factor is going to be that moisture content.
Okay, thank you.
Hi, Jenny. This is for Revive. Do you have OTM50 data yet for your exhaust stack?
We don't yet. So we've been doing some testing. I think right now we're actually working on a project to help define some other methods to go about that. But no, we don't have the data yet. What I would say is what we shared before is what we've seen is very hard to get vapor out of our system. It just doesn't generate it. We need to put it under vacuum. So that's where that permit by exemption. And when we have looked at our vapor GACs, it's been very, very, very little PFAS after a year of operation.
Cool, thank you.
You're welcome.
So, Mr. Richard, you gave us a nice smorgasbord of different destructive technologies out there. If someone's still trying to sort through all of that, what would you say would be, I know you're trying to give an unbiased presentation, but generally speaking, what kind of guidelines or criteria would you recommend somebody use to help sort through, like, what should I use of all these things that are available?
Okay, that's a good question, and I would say in simple terms it becomes very, very site-specific because gasification pyrolysis is a more complex technology which typically involves integration of not only the gasifier, but there's a gas cleanup system, and then depending on your product, you may have a pressure swing absorber to make hydrogen, for example. I think typically the site specifics rule, also because of the infrastructure that may or may not be there, like rail, water supply, electrical grid, and things of that nature. The key thing to note is there is no best technology. Of all the 200 in our database, there is no best technology. Ultimately, the site specifics will be a prominent factor. Secondly, what type of feed are you using? And in this case, because the main purpose of a gasifier or pyrolysis unit is to take the biomass as its key component and then essentially blend in a certain amount of PFAS in some shape or form that will form the feed specification for that unit. And then secondly, what are the product or products that you're going to be making? And all of those have to basically jive with the operating experience of the technologies. And some of the technologies I've shown have been in commercial practice for 30, 40 years, and some have only been in practice for the last 5 to 10 years and have a limited amount of commercial experience. So I'm not sure that answers your question, but there's a lot of complexity to it, and that's why people engage us to kind of look at all the various parameters and sort those out, so it winds up hopefully with a very, very cost-effective system that will take the feed and deliver the products that people are looking for. And in this case, destruction of PFAS as the target component of what you want to use it for.
Thank you.
Is the firefighting foam database that was discussed earlier, and I apologize if I missed it, is that publicly available, or is it accessible in some way?
Not at this point. I have spoken with some of the people over in Michigan, their MPART team. They've also done some data collection, and so I've been able to share with them very high-level information to help inform what they've already collected. What we haven't discussed with Ohio yet is to what extent they would feel comfortable then sharing information. So I'm guessing they won't want to share information about this specific department, this specific product, but maybe that information that we've got, which is, hey, the product that is most common based on number of gallons is X, and here's the other top 10 or 20. We've been using that internally for some of our testing as we develop this set of recipes, essentially, to see which ones to focus on. But we do think that would be helpful for the industry. It's just not our data to share at this point, so we have to just check with Ohio.
All right. Is it happy hour time? All right. Well, let's give our panel another hand. They did a great job. All right. Have fun this evening, everyone.